In the previous lecture, we have discussed in detail Stokes theorem. You have seen by the use of this theorem how we can change the line integral along a closed curve into a surface integral. Now, with the help of this theorem, we will solve some of the important problems to clarify your idea. So, let us see. I have selected some of the important problems to know how the Stokes theorem can be applied in a physical problem. So let us see the first problem. The first problem says if C be any closed curve, then we have to show that the tangential line integral of vector r, that is integral along C r dot dr, is equal to 0. So let us see this problem first of all. I have again written this problem here for your convenience, and we will solve it, or we will prove this result by the help of Stokes theorem. So let us start with Stokes theorem. What the theorem says, we will start from that. So according to Stokes theorem, you know, integral along a closed curve C of f dot dr, this is equal to integral over an open surface S curl of f dot n hat ds, or equivalently you may also write this is integral over S curl of f dot vector ds. This is just the mathematical statement of Stokes theorem. Now see your problem. When you will compare your problem with the statement of Stokes theorem, you will find that at the place of vector field F, there is vector R. So here you can say F is equal to vector R. So let us replace the vector field F by R in this equation 1. Therefore, from 1, after replacing F by R, what will be our result? You can see integral along C r dot dr, this is equal to integral over S curl of f, but now we will write r at the place of f. So this is curl of r dot ds. Now you know curl of r will be 0 because vector r is an irrotational vector. For your convenience, I am just proving that curl of r is equal to 0. So you can find it. Now vector r, you know, this can be expressed as xi hat plus yj hat plus zk hat, and therefore what is curl of r? In determinant form, you can write this as I j k and del x del y and del z, x y z. Now let us solve this determinant. You know In first term there will be I hat and del z by del y minus del y by del z. Actually in second term of determinant there is minus sign, but here I am taking plus. It means the operation will be just reversed. So you can write it in this way. This will be del x by del z minus del z by del x and plus. Now the last term for k, this will be what? You can see easily. This is del y by del x minus del x by del y. Now you know x, y and z are independent variables. So when you will take the partial derivative of z with respect to y or partial derivative of y with respect to z, all these will be 0. So inside the bracket all the partial derivatives are 0. So you can write it 0i plus 0j plus 0k, and you can also say that this is simply 0. So you can see curl of R is equal to 0, and as I have told you, you can write this result directly because you know R is an irrotational vector, and if R is irrotational, definitely its curl will be 0. So this result implies that R is an irrotational vector. And now you can see from your equation 2, since curl of R is 0 and this is a definite integral, so in this case the integrand is 0, and you know if the integrand is 0 and the integral is definite, definitely the result will be 0. Therefore from equation 2 you can say that integral along C r dot dr is equal to 0, and this is the result which we have to prove. So you can see how easily such type of problems can be solved by the use of Stokes theorem. Now the second part of the first problem is that we have to show the integral along the closed curve C of gradient of phi dot dr is equal to 0. So now let us try to solve this. You can also easily solve this problem by the help of Stokes theorem. So in this theorem we have to show that integral along C del phi dot dr is equal to 0. This is the result which we have to show. So here if you will compare this problem with the Stokes theorem which we have mentioned in this equation 1, you can easily see that at the place of the vector field f there is gradient of phi. So here we can say here f is equal to del phi, and therefore by the use of Stokes theorem you can write integral along C del phi dot dr, this will be equal to integral over the open surface S curl of f, but f is here del phi. So del phi means grad phi. So this is grad phi dot ds. But you know the vector identity that curl of gradient of any scalar function is always 0. So you can say curl of grad phi is equal to 0, and therefore we can say that integral along the closed curve C of del phi dot dr, this is simply equal to 0. So in this way you can prove this result very easily by the use of Stokes theorem. Now let us see the next problem. In next problem we have to verify Stokes theorem for a vector field defined by f equal to x square minus y square I plus 2xyj, and the region for which we have to verify this Stokes theorem is actually a rectangular region in positive xy plane bounded by the lines x equal to 0 and x equal to a and y equal to 0, y equal to b. It means the surface along which we have to take the integral is just a rectangular surface lying in xy plane. So let us try to solve this second problem. So let us see. First of all, we will show in figure the rectangular region which have been defined in this problem. So let us take this x-axis and y-axis. Since the region is lying in positive xy plane, so I am showing this region in the first quadrant of here. So let us see, this is your rectangular region. Let this is OABD. OABD. Now this line OA is defined by the equation y equal to 0. AB will be defined by the equation x equal to a, because here the coordinates of point O is 0, 0 and that of point A is A0. So for AB, x is constant at the value A, and this line BD is defined by the equation y equal to b, and OD will be defined by the equation x equal to 0. So this is the rectangular region R which have been shown in this figure, and this region has been defined in your problem. Now it is given in our problem that the vector field along which we have to find for which we have to verify Stokes theorem is what? The problem says that the vector field F is equal to x square minus y square I plus 2xyj. This is the vector field. Now you know, for this vector field, if we have to verify the Stokes theorem, we have to show that the LHS and RHS of Stokes theorem are same. So according to Stokes theorem, integral along the closed curve C. In fact, this closed curve OABDO, this is actually your closed curve C. So along this closed curve C, we have to show that f dot dr is equal to integral over S curl of f dot ds. We have to show this, and for this we will evaluate this tangential line integral defined in LHS of this equation 1 independently by the concept of evaluation of tangential line integral. and after that we will find the RHS of this equation, and if the two values will be same, then you can say that Stokes theorem is valid for this vector field. So let us try to evaluate the LHS by independent method, which we have learnt in the study of tangential line integral. So for this, first of all, we will find the value of f dot dr. So now you know r is equal to xi plus yj plus zk. But since our surface is lying in xy plane, so you can take this z equal to 0. So r can be written simply as xi plus yj plus z plus 0k, that is 0, or any constant value of z you can also take, and therefore dr will be what? This will be simply dxi plus dyj, and therefore f dot dr can be easily found. Let us see. F is given here. This is x square minus y square I plus 2xyj. This is your f, and dr, as you can see, we have obtained this dr is dxi plus dyj. So let us take the scalar product of these two vectors. You know the scalar, in a scalar product similar term will remain, but all the dissimilar term vanishes. So this will be simply equal to x square minus y square dx plus 2xy dy, and let us say this is your equation 1. Now we will find the tangential line integral of this f dot dr along the closed curve C. Here the closed curve C means OABDO. So we can see what will be this integral. So therefore integral along C of f dot dr, it means integral of f dot dr along the curve OABDO, and you can see this integral can be written as f dot dr along OA plus integral of f dot dr along AB plus integral of f dot dr along BD, and plus integral of f dot dr along DO. You can see this figure. We will take integral of f dot dr along OA, then along AB, then along BD, and after that along DO. And when you will add all these integrals, you will get the integral along the closed loop or closed curve OABDO, which is actually C. So let us say this is equation number 2. Now we will evaluate each and every integral in the RHS of this equation separately. So first of all, along OA, see, along OA. See the figure. When you will move along OA, you can see x varies between 0 and a, but y remains constant at a particular value which is 0. So for this path OA, you can say 0 is less or equal to x, and this is less or equal to a, and y is constant, and this constant value is 0. Now since y is constant, so you can say that dy is equal to 0. dy equal to 0. And so you can see what will be the integral of f dot dr along the path OA. See the expression for f dot dr. This is this much, x square minus y square dx plus 2xy dy. Since dy is 0, so this second term will be 0, and y is also 0. So the first term will be simply x square dx, only x square dx. So in this integral may be written as simply integral of x square dx. And what are the limits of x? You can see the lower limit of x is 0 and the upper limit of x is a. So limits are 0 and a. So this will be simply x cubed by 3, and limits are a and 0. When you will put the limit, this will be simply 1 over 3 a cube. 1 over 3 a cube. And this is your equation 3. Now we will evaluate the second integral in RHS of equation 2. So for this we will see what will happen when we will move along the path AB. So you can say along AB, along the path AB. See the figure. When you will move along the path AB, you can see x remains constant at a particular value a, but y varies from 0 to b, because the coordinates of this point will be what? This will be a, b, AB. And coordinates of this point D are in fact 0, b, 0, b. So along the path A, x is constant and that constant value is a, and y varies between 0 and b. So you can say along the path AB, what will happen? 0 is less or equal to y, and this is less or equal to b. And at the same time, x is constant at the value a. Now since x is constant, so you can say dx is equal to 0. Now see this equation 1. Since dx is 0, so this first term in the expression for f dot dr will vanish, and in the second term x is equal to a. So this will be 2ay dy. 2ay dy. Therefore, you can write that the integral f dot dr along AB, what will be this? See here. Since you have seen that this will be equal to 2ay dy, and the limits of y are 0 and b, as you can see here. So this is 0 to b. Since 2a is constant, it will be outside of the integral, and integral of y will be y square over 2, and limits are b and 0. Now put the limit. You can see this 2 and this 2 will cancel out, and this will be simply ab square. ab square. So we have evaluated this integral 2. Now we will evaluate the third integral, that is integral of f dot dr along BD. So you can see what will happen along BD. Along BD. See the figure. When you will move from B to D, see here, y remains constant at a particular value B, but x varies from A to 0 because the x coordinate of point B is A, you can see, and that of the point D is 0, so x varies between A and 0. So along the path B, you can say A is less or equal to x and this is less or equal to 0, and y is fixed at a particular value B. Now since y is constant, so you can say that this dy is equal to 0. So in this condition, what will be the value of f dot dr? You can see, since dy is 0 in this case, so this second term will vanish, and y is fixed at a value b, so this will be x square minus b square dx. So let us use this idea here. Therefore, integral of f dot dr along BD, this will be equal to integral x square minus b square, since y is b, dx, and limits are actually a and 0. You can see the lower limit for x is a and upper limit is 0 here. Mark this. Now we will try to evaluate this integral. You can see this is a very simple integral. This is x cube over 3 minus b square x minus b square x, and the limits are a and 0. A and 0. So in this condition, what will be our values of this integral? You can see this will be a cube by 3 minus ab square, and sorry, the limits are not 0 to a, but it is a to 0. Limits are, so you can take here minus sign and then you can make the limits 0 to a. So this will be actually then what? Then this will be minus this much, and that will be equal to minus a cube by 3 plus ab square, and this is equation number 5. So we have evaluated the integral of f dot dr along BD. Now finally we will evaluate the integral of f dot dr along DO. So you can see for DO or along DO, you can say, see the figure. When we will move from D to O along this line DO, you can see x remains constant at a particular value 0, but b varies from y varies from b to 0. So for this path, b is less or equal to y, and this is less or equal to 0, and at the same time you can see x is constant and this constant value is 0, and therefore dx will be equal to 0. So now see the equation number 1. Since in this case dx is equal to 0, so this first term will vanish, and x is also constant at the value 0, so the second term will also vanish. So for this path DO, f dot dr is equal to 0. Therefore, f dot dr in this case is equal to 0, and so if you will take the integral of f dot dr along the path do, that will vanish, that is also equal to 0. So in this way you can see we have evaluated all the integrals defined in the RHS of this equation 2. So substituting all these values of integrals in equation 2, we can find what will be the integral of f dot dr along the closed curve C. So you can easily find it. Therefore, from equation 2, find the value of integral along C of f dot dr. What will be this? For this you have to add all the integrals which you have obtained. This will be 1 by 3a cube plus ab square plus minus a cube by 3 plus ab square plus 0. So let us add all these values. So this will be 1 by 3 a cube plus ab square minus 1 by 3 a cube and plus ab square and plus 0. Now you can see this 1 by 3 a cube will cancel out, and this will be simply equal to 2ab square. So we have calculated the value of this tangential line integral along the closed curve C, bounding the region defined in xy plane in our problem by independent method, by the technique which we have learnt in the study of evaluation of tangential line integral. Now we will see, according to Stokes theorem, this tangential line integral is equal to what? This is equal to surface integral of curl of f over the surface S bounded by this closed curve C. So now we will try to find what will be this integral defined in equation 1. So for that, first of all, we will have to find the value of curl f. So now you can see what will be curl of f. Again, you know curl of f is defined as the determinant of I, j, k del del x del del y del del z, and here will be fx, fy and fz. But according to our problem, fx is equal to x square minus y square, fy is 2xy, and this fz is 0. So you should write it in this manner. This is I, j, k del del x del del y del del z, and fx is x square minus y square, and fy is 2xy, and fz is 0. So now let us solve this. You can see this will be del 0 del y, that will be 0, and minus del 2xy del z. Del 2xy del z I plus, again I am taking plus here, so you can see this will be del z x square minus y square, and minus del 0 by del x, that will be 0. This is j, and plus, now the third term, this will be del x 2xy, del x 2xy, and minus del y x square minus y square, del y x square minus y square k. So now you can see the first term will be 0, because here we are taking the partial derivative, and here we have to differentiate partially xy with respect to z. But since x and y both are completely independent of z, so this term will be 0. Again you can see in the second term we have to take partial derivative of x square minus y square with respect to z. That will be also 0, because x and y both are independent of z. So only the last term will remain, and here we have to differentiate 2xy. In fact, I am writing here the last term. You can see the last term is, because here it is not very clear, so this will be del x 2xy minus del y x square minus y square, and you have to take here the unit vector k. Now the derivative of 2xy with respect to x, this will be simply 2y minus, and again here I am differentiating it with respect to y, so dc of x square will be 0, and that of y square will be 2y. So this will be minus minus plus, that is plus 2y k, plus 2y k, and so this is simply 4y k. So in this way you can see we have evaluated the value of curl of f, which is equal to 4y k. Now you can take the value of ds will be equal to what? For this you can see the region which is defined in our equation. Since OABD is the region in positive xy plane, so ds means an elementary area in positive xy plane. So this is your elementary area, and this elementary area ds will be equal to what? You can see easily. This is actually equal to dx, and this is dy. So actually this ds will be simply equal to dx into dy. Since this element is lying in xy plane, so area vector ds will be in z direction, because you know the area vector of any plane surface is normal to the surface, and since this ds is in xy plane, and on xy plane x-axis is normal, so this ds vector will be in z direction, that is along the unit vector k. So you can say that ds vector is equal to dx into dy k. So getting this idea, you can now easily find what will be the surface integral over S of curl of f dot ds. What will be this? As you can see, we have obtained the value of curl of f here, which is 4yk. So this will be 4yk, and you have seen that this elementary area vector ds is equal to dx into dy k. So this is equal to 4 k dot k is 1 and 4 is constant. Now here variables are x and y, so we will take the limits of variable for x and y, and those limits you know are 0 to a and 0 to b. So x will vary from 0 to a and y varies from 0 to b, and this is y dy dx. This is a very simple double integral because both the limits are actually constant, so you can do it very easily. This will be 0 to a, and the integral of y will be y square by 2, and the limits are b and 0, and this is dx. Now you can see this will be 2 integral 0 to a, and this is b square dx, and this will be equal to 2 b square x, limits are a and 0. So this is simply 2ab square. So you can see that integral over s of curl of f dot ds is equal to what? You can see we have obtained this is 2ab square, and say this is equation number b. This is equation b. Now you can compare the equation a and equation b. In equation a, you can see this tangential line integral is equal to 2ab square, and in equation b, this surface integral is equal to 2ab square. So from equation a and b, you can easily say that integral along c of f dot dr is equal to integral over s of curl of f dot ds, and you can see this is nothing, this is simply a Stokes theorem. So you can say the Stokes theorem is verified. So a Stokes theorem is verified. So you can see I have solved some of the important problems, but getting these ideas which we have learnt in this lecture, you can solve several problems like these problems from your textbook, and you will find that these problems are very important for university examination and also for different standard competitive examinations.